Okay, so the topic for today is solving systems of equations, and we're going to solve ones that don't have one point of intersection as their solutions, but either do not intersect, so they have no solution, or a system of equations where the two equations are actually equations for the same line. And so our first example here is actually a system with parallel lines. Now, parallel lines never intersect. And so remember, our solution is the point of intersection of two lines. Well, if they don't ever intersect, there is no point of intersection and there is no solution. And so these two equations, when we solve them as a system, is going to have no solution. But what I want to show you is what kind of answer you're going to get when you try and solve this, because when you're solving a system, you're not going to have a lovely picture next to it that shows two parallel lines and you say, oh, well, they don't intersect, so they have no solution. You're going to be doing this algebraically and you're not going to know what's going on. So what I want to do is go ahead and solve this using one of our normal methods. We can either use substitution or we can use elimination. It doesn't matter. And what's going to happen is we're going to get kind of an unusual situation to occur. But once you see this, you'll know what to do with this. First of all, I've got two equations here. And what I want to do with these is to solve this system. Now, this is set up beautifully for substitution. Because I have y equals a number. So substitution would be very simple here. However, I could also use elimination if I rewrite this second equation so that it is in the same form as the first equation. So let's go ahead and use the substitution. So I'm going to put 2x plus 5 in place of y in the second equation. So I've got 6x minus 3 times 2x plus 5 equals 6. All right, and I'm going to go ahead and distribute, and that gives me 6x minus 6x minus 15 equals 6. And when I combine my terms, the 6x and the minus 6x actually are going to cancel, and I have no x's left. So now I have negative 15 equals 6. And that is not a true statement. That's a false statement. Now, the fact that all of my variables canceled out alerts me to the fact that one of two things is true. Either this has no solution because it's parallel lines, or it's actually the same line. Since the two numbers I'm left with are different, this is two parallel lines. So this is parallel lines, and there is no solution. Now, I would like to show you what it's going to look like if you had used elimination as your method to solve the system of equations. If we did that, we would take this second equation and simply subtract 2x from both sides. So I would have negative 2x plus y equals 5. And now to create an elimination, let's say I could multiply that second equation by 3. And I could eliminate my x's. So I'm going to take the second equation and multiply by 3. The top equation, I'm not going to do anything with this. So I'm going to rewrite it the same way it was, which is 6x minus 3y equals 6. And the second one, when I multiply it by 3, is negative 6x plus 3y equals 15. Now, when I add these two together, the x's eliminate and the y's eliminate. What I have left on the left-hand side, since everything eliminated, is 0. And on the right-hand side, I have 21. So again, you'll see that all my variables canceled out, and I'm left with an equation. Since the two sides are not equal, this is a situation where we have parallel lines and there is no solution. All right, so the result that we got, it's either here or here. Negative 15 equals 6, which is false, or 0 equals 21 is false. The system has no solution. These two lines are parallel. All right, let's go ahead and go to the next page, page 7, and we have an example at the top of the page. This is a situation where you have two equations for the same line. And you don't notice that because one's written in slope-intercept form and one is written in standard form. All right, so they don't look like the same line. So you're not necessarily going to notice. But in fact, in this case, they are the same line. Let's talk about if the two lines are the same line. Essentially, what's happening is you're drawing the two lines right on top of each other. And the solution is not like it is when we had a linear equation and we had the situation come up and we said the solution was all real numbers. Well, it's not all the points. Because here's the issue. If you have a point out here, this is not a solution. Because it is not on the line. The issue is that all the points on the line are solutions. So when we state the solution for this type of a system, we're going to say all points on the line, and we're going to identify it either with this equation or this equation. Doesn't matter which. But we're going to identify it as one of the equations. And I'll show you how we'll do that when we go through this problem. So here's what I'm going to do. Since typically most of us end up using elimination as opposed to substitution because we're going to get so much more practice with it, let's go ahead and we're going to do this one with elimination. I need them both to be in the same form, so what I would do here is subtract 3x from both sides. And what I would get is negative 3x plus y equals negative 6. And now I'm looking for a way to create an elimination between these two equations, which still do not look alike. All right? And what I would do is to eliminate x, I might multiply the top equation by 2. So I'll draw an arrow, multiply the top one by 2, and we'll leave the second one alone. So with the top one, I have negative 6x plus 2y equals negative 12. And the bottom one stays the same. 6x minus 2y equals positive 12. Now notice what happens when I add these two together. The x's eliminate, the y's eliminate. So what I have remaining on the left-hand side of the equation is 0. And even on the right-hand side, negative 12 and positive 12, that is 0. So what I'm left with is 0 equals 0. 0 equals 0 is a true statement. So that's telling me these two equations are actually the same line. There's no difference between the two. All right? So these are the same line. Here's how I'm going to write my solution. My solution is all points on the line, and I need to identify it. I can use either this equation in slope-intercept form, this equation in standard form, or this equation in standard form. Doesn't matter which. So I'm just gonna say y equals 3x minus 6. And I've always got to state which line all the points are on. It's not just all points, it's all points on a specific line.